Welcome back. We're continuing here, and now we're going to begin to talk about the principle of conservation of momentum, okay? It says that total linear momentum in a closed system remains constant in both magnitude and direction. And of course, that tells you again or reminds you that momentum is a vector quantity. So we express it in both magnitude and direction. So from this principle here, from this statement here, we can unpack it mathematically and say this means total momentum before in a particular system will always be equal to total momentum after if that system is closed, if it is isolated. Okay, now from this principle, we come up with this formulas here. If we're looking at two objects that are colliding, okay, they can collide. At first here, object 1 is moving on its own, object B is moving on its own, okay, with their initial velocities. They can collide, and after collision in that system, this is total momentum of that system before, and that equals to total of momentum of the same system after that collision. So we can express it that way. Now this formula here shows a situation where objects separate after collision. Okay, so they separate after collision. Now there are situations where objects will move together after collision. So you have got total momentum before equals to total momentum after, where the two objects share the same velocity. Now when they share the same velocity after that collision, it means V final is the same for both of them. You can work it out in that way. We can also have situations where we're talking about explosions, where objects were together before, okay, so they had the same initial velocity, but something happens, some kind of an explosion happens, and they separate after collision, and therefore that gives the total momentum after, which is their final. So this is momentum before equaling momentum after in that way. Okay, now when these collisions occur, we have got different types of collisions. Basically two of them. We have what we call elastic collision and inelastic collision. What is the difference between them? Elastic collision is one where the total kinetic energy of the system is conserved. In other words, EK of A plus EK of B before should be equal to EK of A plus EK of B after. This is when we're talking elastic collision. The kinetic energy is conserved. But when we talk inelastic collision, which is the one more likely to happen, because this is now realistic, we have very, very little chances of conserving kinetic energy during motion. So when collisions occur, this inelastic collision is one where total kinetic energy of the system is not conserved, so the kinetic energy is lost into other forms here. So we see it converted into heat energy when that impact happens, to sound energy, the bang when collisions occur, and then light energy. Okay, you would see during that friction some light comes off. Okay, so it's kinetic energy being converted to light energy there. So that's what happens. Now let's have a look at this example here quickly to see how we can apply the principle of conservation of momentum. A railway track A of mass 2,000 kilograms moves westwards with a velocity of 3 meters per second. It collides with a stationary track B of mass 1,200 kilograms, loaded with electronic equipment of mass 300 kilograms. The two tracks combine after the collision. Ignore effects of friction. Okay, now this is the system, the situation. This one, let's take westwards to be positive now. Okay, so that direction is positive. And this one is stationary, 0 meters per second. Okay, this one is moving that way to the left, westwards at 3 meters per second. Total mass here of B, we will take it to be 1,500 because of that load there. Okay, so this is before collision and this is after collision. Right, now, write down the magnitude and direction of the reaction force to the weight of track A. Now, if you look at track A, the weight of track A is in that direction, force of gravity. The force that reacts to this is what we call the normal force, the force that acts from the surface where that object is, F normal, and it should be equal to Fg. Fg is mass times G, so this is 2,000 times 9.8. So you can write that down, 2,000 times 9.8, okay, and it's 19,600 newtons. That is the weight. So the magnitude of Fn, of that force, when you're answering this question, you should write it down as, because they only want magnitude. No, they also want direction. So we'll say 9,600 newtons upwards. Okay? Because it is against the force of gravity. Let's meet in the next section.